Everyone, we'll go ahead and get started. Thank you back to the Thursday Scientific Seminar Series, and it is my pleasure today to introduce Dr. Colin Beier, who I met when I first started at Carey way long ago when he was here working predominantly with Peter Groffman and had been working with the Hubbard Brook group. Dr. Beier is an associate professor at SUNY ESF, which is just up the road for folks who haven't been there. It's worth a trip, where he is in the Department of Sustainable Resources Management and expert in socioecological forest systems, and I think we're going to hear a lot about that today, so I won't go into details and give you more time to share. I'm really excited to hear more about our local Adirondack Park and carbon storage in New York and more broadly. So with that, thanks for coming.
You guys can hear me? Excellent. All right. It's a pleasure to be back at Carey. I think of this as one of the meccas for ecologists, and you guys have definitely had a glow up since the last time I was here. Really beautiful facility and a lot of new faces. Nothing against the old faces, but the new faces are exciting to see, and especially to see so many diverse faces more, I think, on the staff here is really exciting. I'm really grateful to be here to share with you some of this work and just to give you an overview of this effort that we've undertaken for the last few years for New York State. And this is just a quick overview, and I won't go through everything here right now, but the upshot of a lot of this work is the ability to be able to deliver basically the kinds of information around forest carbon dynamics and greenhouse gas inventory, but at scales that are relevant for decision making. And we do that through maps, right? And of course, yesterday I realized I had none of my Mac adapters, so I'm zipping through this beautiful part of the state, eventually ending up in Poughkeepsie at the mall to buy a $75 Mac adapter. But my map is very important for helping me get to where I need to go. For some reason, it took me through downtown Poughkeepsie. But anyways, that's Google for you. But this is the upshot of a lot of what we were aiming for, which is a stock change map, but I'll get to that here. And touch on a number of things, but I have to give you a few warnings. First of all, a few cautions. At ESF, we are the State College of Forestry. That is our roots. We are a facility and an institution built to support state and other environmental stewardship decision making. And that's certainly a big focus of my lab's work and the kind of work that we like to do. We do have fundamental scientists. I know that this is a place where a great deal of absolutely fundamental ecological research takes place. So I wanted to warn you, this is very applied work, okay? It also involves data mining, right? Which maybe I'm coming from that old school, but I was still part of that old school. I was taught as an ecologist, this is the greatest sin we can commit as ecologists. Of course, times are changing, but this is modeling for prediction. And I also, because I want to cover a lot and try to give you a gestalt of what we've done and how I think it might be useful in some of the things that we've done, I'm not going to get into a lot of the gory details, but we have them, and I'm happy to do that if anybody would like to. And we're publishing this work in the literature as we go. With those warnings set aside, right? New York State has passed one of the most ambitious climate laws in the world to be net zero emissions by 2050. And fundamentally, that means an 85% reduction in emissions and a 15% offset. Who's going to provide the offset? Our forest lands, implicitly and explicitly in the scoping plan, are expected to provide roughly 60 million metric tons of CO2 equivalent of carbon storage every year by 2050 and afterwards to offset that hard to decarbonize sectors of our economy that are largely in the city downstate, but are other components as well. We are currently, as of 2021, not even halfway there. How do we know that? Well, I'll mention that in a minute. How do we get to where we need to be, or at least we move there? We do that through natural climate solutions. These are the three primary strategies identified by Nature Conservancy, U.S. Climate Alliance, and other groups who have really done tremendous work, Joe Farjone and his team, and others who have done incredible work here on natural climate solutions and raising the profile of these. This is reforestation, this is avoiding conversion or avoiding deforestation, and the much more complex and broader one of changing or adjusting how we manage our forest resources. Well, who's doing this? Individual landowners, right? And this is a complex landscape, right? The vast majority of forest lands, about 2/3, a little bit less than 2/3 of the state, depending on how you define forest, is forested, right? The vast majority of that is owned by people like you and I, right? With small wooded parcels, right? The vast majority of this land is held by, right, non-industrial landowners in small parcels, often in sizes that have been historically considered to be not operable from a forestry standpoint. They're too small. Right? And there's a lot of patches and fragments, and it's a very heterogeneous landscape. And it's a beautiful landscape, but it's patchy and it's complicated, right? And so looking at this situation, right, how do we get to 60, or how do we move that needle, right? How do we implement these practices across this landscape when all we had going into this were these beautiful tables produced by the Forest Service, right, these very intuitive tables. Again, I always like to joke with Grant. Grant Domke is a great partner and collaborator. This is what he produces. He doesn't love these either, right? Occasionally, they'll allow him to produce something even more intuitive, like a graph, right, that compares all the states. But this is the state-level greenhouse gas inventory, the IPCC Tier 3, right, the stock change methodology for the states that FIA does with their data. Our whole goal was to take this and not substitute or replace it, but to extend it. It's meant to be an extension of what FIA does into a map space, right? So to translate this stock change methodology from this tabular state-level information into maps, right? Super easy, right? No big deal, right? And of course, it was easy to pitch this and write the proposal, and then when we got it, I was like, are we actually gonna do this? The overview of what we eventually developed is an integrated platform, right, for doing both the assessment, the inventory, and stock change, but also which is shown in the green here, and then the ability to do monitoring on top of that as time goes on, as well as, and I'll touch on very briefly here, because I'm still an ecologist and forecasting still makes me very nauseous, but on the ability to forecast the future, because it is really about what's going to happen in the future, especially when it comes to carbon sequestration. What we've tried to do here is, and what we have achieved, is that we built something that is very extendable, very applicable to other places. It's built on freely available data, FIA, Landsat, other sources, right? And completely open source tools. So all of this is built with R and Postgres. We're using Google Earth Engine. We're using a variety of tools to leverage this freely available data that exists for all of CONUS and for many other parts of the world. This is, my metaphor for this is a first generation Prius. Toyota didn't invent the gas engine or the electric engine. They didn't even invent regenerative braking or a really ugly design that would tell people you're really slow, get out of the way, right? But they put it all together into a really nice package that ran, right? You'll still see these on the road, right? They got you from point A to point B, and that's desperately what New York State needed, and arguably other places do too. So that was our kind of guiding principles here. We're trying to bring all this together. We're certainly not the first, by any stretch of the imagination, to do this kind of modeling, where we're bringing together field and remote sensing data to produce maps. What we have been trying to do is really target this in a direction that has applications and end uses, and hopefully, if we do well enough, some of the data that we produce and some of the maps and things can generate insights and directions for fundamental research to address some fundamental questions as well. And I'll get to some of that at the very end. Another way of looking at this is a daisy chain of models where we first look at current forest biomass, which we've done with LiDAR, as well as Landsat, and I'll explain that in some detail. Then we have to go back in time. We have to go back in time because we not only have to say what are the stocks now, but what are the stocks in the past. And for CLCPA, the benchmark year is 1990. So we said, well, if we can get back to 1990, that would be great. right? Based on that, we need to then, once we model biomass, we need to think about how that relates along with other landscape variables to actual carbon stocks, right? Then we look at how carbon stocks are changing over space and time, and then we bring all of that into a variety of accounting, monitoring, forecasting types of applications. So it is a daisy chain of models, modeling unmodeled, which also, right, makes me a little nervous. But we do dig into this a lot, and a lot of uncertainty, as I'll show you, and try to understand what we know and what we don't know from this process. So we started out with LiDAR. This is airborne laser scanning. This is the same technology that gets you a speeding ticket, basically. Laser bounces, shot down from the plane, bounces off the ground, bounces off the trees. LiDAR gives you a three-dimensional representation of the landscape, and it is really the best remote sensing data source out there right now for modeling above-ground biomass across large areas. Of course, in New York State, because of our very small economy and limited economic power, right, we only have a very weird patchwork of LiDAR data, unlike Massachusetts and Pennsylvania that have paid for statewide. We have this patchwork, the spatio-temporal patchwork of LiDAR. Now, since then, and I might show you, I'm not sure, these areas have largely been filled with some FEMA data from 2020 that was delayed for some time. But when we set out on this, this is what we had, right? And we had the FIA plot locations, right? And we brought that data together. We said, well, we've got these point clouds we've clipped out by the FIA plots, right? And we calculated a whole bunch of predictors from that. And we trained machine learning models, things like random forest, gradient boosting machines, support vector machines, right? And we basically developed above ground biomass models, right, using LiDAR wherever we had it, right? And I want to mention that it was a huge data engineering challenge just to align the FIA plots, right, which are measured every 7 years in New York State, with that snapshot of LiDAR when they flew over. And this is all leaf-off LiDAR, which would seem counterintuitive that leaf-off LiDAR is actually useful, but leaf-off LiDAR is great because you get a really nice ground return, which means your estimates of the heights of all of that stuff that's bouncing off the vegetation are really accurate, and that turns out to be really important and helpful. So leaf-off LiDAR is actually leaf on and leaf off at the same time, well, not the same time, but within the same time frame would be ideal, but we do what we can. So we've used these machine learning models to map forest above ground biomass for the LiDAR year at 30-meter resolution. This is a portion of the southeastern Adirondacks to show you. You can see in the reference map here. So Lake George, Scroon Lake. I have a pointer. I keep pointing with my finger as if you guys can see where I'm pointing. I'm sorry. Right, so here's Long Lake. Here's Huntington Forest. ESF's 15,000 acre property. We have 25,000 acres in the Adirondacks. We only have 14 in Syracuse, but we make up for it elsewhere, right? Huntington Forest, and you'll see this area again. This was one of the places that we kind of smell tested our maps because I worked there for years and I know exactly what things look like over there, right? But we have this above ground biomass map, and I am showing you water and developed. We're not mapping in those areas. We do have data for those areas, but we've masked them out for a variety of reasons, mainly just for interpretation, right? But of course, it's a bunch of puzzle pieces, right? We got all these different things representing different years. So here's, we went from a very forested landscape. This is Cayuga, Oswego County, Finger Lakes, getting up into the Tug Hill, but a very fragmented landscape. You've got Allegheny-Steuben, which includes Allegheny State Park, which has the highest biomass in the state for an FIA plot. And of course, we've got this region here, right, which includes Poughkeepsie and Dutchess County. We're somewhere over here in Millbrook, right? And of course, right, the very southeastern Catskills, right? But that's from 2014, right? I want something newer than that, right? The reality is LiDAR gives us incredible accuracy of these models, right? When we go back and compare these models to what else is in the literature, there's nothing that's better, and right, it gives us really good accuracy. But in time, there's a disparity amongst sensors. We had intensity variables that we wanted to use that actually improved our models even more, but the variance between the values between the missions, because different sensors were used, made it impossible to use those data, even with a machine learning model, which can tolerate some pretty crazy stuff that like a regression model would really struggle with. Right? There's very limited areas with multi-temporal coverage, so we don't have an idea of how things are changing. and it's computationally intensive. In the last 4 years, my lab has processed about 36 terabytes of LiDAR, right? I'm doing all of this on Amazon Web Services, right? In case you didn't know it, ESF doesn't have a supercomputer, right? So we process through a lot. It's very rich information. It's really valuable. But at the end of the day, the LiDAR maps alone are not sufficient for our needs. So we have a patchwork like this, and we've filled in much of the rest of the area of this patchwork. I just don't have it ready to show you yet. But you can see, like, I mean, it's just classic, like entire Hamilton County, 67% forest preserve, right? Almost entirely forested, just gone, just not there yet. And when they did fly this LiDAR, they flew 2/3 of it in July, which I don't know if you guys know, but the leaves are on the trees in July, right? So we can't use it, right? And so this is why I think it was delayed several years. So this is good, but not great, because it doesn't really get us what we need. We can make some pretty maps, right? By the way, I just want to point out, just to take a little sidestep, LiDAR is really cool, right? And I think everyone maybe knows that. I'm showing you several canopy height models superimposed upon satellite imagery. This is for portions of southern Onondaga County in the Tully area, right? You can see the ground, the blue, right, scaling up to green and to red, right, is the height of that vegetation. So the detail with which you can map and understand vegetation structure with this LiDAR, this is a 1 meter canopy height model. It's a side product of what we get when we produce this. What's more important is this is the land that the state is giving the Onondaga Nation back again, right? Hopefully the first of many chunks of land that should be returned to the Onondaga. I live on Onondaga territory. It is unceded land. It actually should have been returned to them in 1990, right, by treaty, but of course we have a pattern of not honoring those treaties. But I'm honored to be able to work with my partners and with my friends on the nation to map for them the resources they're getting back again with the kind of detail that they never could have imagined, right? And this is helping them restore brook trout habitat and a lot of things, wild ginger. So these things have real world applications, and the excitement that they have about being able to have these resources is really powerful. So I just wanted to mention that because it's something that I'm really excited about. All right, back to the boring stuff. So Landsat, right, gives us advantages that LiDAR doesn't. Landsat takes us back in time, it's continuous. And so our next stage of approach was to train two types of models. Directly trained Landsat variables, Landsat spectral information, processed with a temporal segmentation algorithm called LandTrender. This is implemented on Google Earth Engine. It's all right there for you. Like it's all right there. You don't have to store all the imagery. You can do a lot with this. It's really powerful. It's great work by Rob Kennedy's group to build this. So we trained directly on FIA plots. This is these direct models. We also trained the same Landsat predictors on our LiDAR AGB maps that I just showed you by stratifying a selection of about 80,000 pixels from those maps, right? So we've got a few thousand FIA plots in New York State, right? We've got about 4,500 and about 2/3 of those are forested roughly. You know, we have millions and millions of pixels to train on, right? But we train these two different sets of models and then we ensemble them together into an ensemble model. And we did this for a couple of reasons. We do have to go back in time, so we have to do something based on Landsat. But one of the things that you often see is AGB models have a saturation threshold, right? They have a false ceiling. So the highest value for AGB, above ground biomass in New York State based on an FIA plot, is in Allegheny State Park. It's 425 metric tons per hectare, which is probably an allometric error, right? It's probably a bit higher than reality, right? The vast majority of New York State forests are under, 99% of them are under 300 metric tons per hectare, okay? Our LiDAR models get right to that threshold. So our LiDAR models are incapable of capturing that upper 1 percentile, right? A pure Landsat model, just trained directly on these plots, saturates at 220. This has implications not only for mapping more biomass, heavier, more developed forests, also has implications for as your forests mature into that space, can you capture that and that continued growth and sequestration? You hit a ceiling, it flattens out. That's a problem. That's a real problem, right? Maybe not as much in the Adirondacks, but certainly down here in the Hudson Valley and in the Catskills. Forests don't tend to get that big in the Adirondacks, right? Conditions are tough there. Conditions are a little better here, and you've got a lot of oak and hickory that change the game a bit down here. Training on LiDAR AGB lifts this threshold, right? And it brings us up from 220 to about 280 in the model, in the ensemble model. So that less than 2% of New York State forests are above 200 metric tons per hectare. So we are still missing some, but it's not too bad, right? It also improves the fine scale patterns, and I'll show you this really briefly. So this is Huntington Forest, so here's Catlin Lake, right? Over here, we're getting, this is High Peaks Wilderness up here, Santanoni in particular. This is Rich Lake, you can see Route 28 running through here, right? And what this is showing is the Landsat predictions, which have a lower plot to pixel error, but a very low prediction ceiling, versus the LiDAR predictions for the same area, higher prediction ceiling and better fine-grained pattern. And one of the things that LiDAR picks up that Landsat does not do well is down here in this area by the Cold River, just north of Huntington Forest, we have some very big stands of white pine, and it just does not pick them up. This guy doesn't pick them up here, but the LiDAR, because it picks up that height, it picks up that white pine, and that makes that prediction much better. And I've been there, and some of you may have been there too. There's big trees over there, okay? And so in this area over here, right, this is just an example of where this fine scale pattern, you can also see some of the edges between the working forest land here, right, and other lands, including Huntington Forest. This whole area on this edge of Huntington here is never been cut. It's one of the few places in New York State that was never logged over. And you can see the edge between that and the working land very crisply with the LiDAR model. So this hybrid ensemble combines the direct and indirect. It tries to combine the best of both worlds, right? Using an ensemble that tries to achieve a good balance between our overall accuracy when we test back against FIA again, as well as the prediction ceiling and the fine-grained pattern, which is more of a qualitative thing, right? So we're trying to seek a balance here. And you could seek and identify a different balance, but this is what we did. So we have an AGB modeling platform that now gives us the ability to go back to 1990 and make annual wall-to-wall 30-meter predictions across the state. Great, that's AGB. What about carbon? Well, the conversion to carbon from AGB depends on the pool. There's 5 carbon pools, right? There's 2 in vegetation, which are above ground and below ground carbon, and then there's soil, litter, and deadwood, right? In most forests in New York State, the soil carbon pools, although the data quite honestly stinks, right? But the soil carbon pools are as large, if not larger, than all other pools combined, right? We can directly estimate from our above ground biomass what that AGC and BGC, that above ground carbon and below ground carbon and vegetation is. It's a simple conversion, right? Based on forest type, right? Or you could just use Woodall's 50%, right? However you want to do it, right? We had to use phase 3 FIA data where they actually measure soil litter and deadwood and do our best to model those across the landscape. And again, some of that was driven by the need to cover all 5 carbon pools in this project. And I'll point out at various points, or I'll try to remember, that while the live carbon, the AGC, BGC, the carbon in vegetation is very dynamic, and we use those dynamics, for the most part, we're holding 30-year means of soil litter, especially soil litter and deadwood, because our models really, we just don't have the data to capture variation in that. And any trends that we would see in soil carbon are certainly not represented mechanistically in any way, shape, or form by the data that's in these models. The reality is that soil carbon does not really correlate with above ground biomass very well. It's much more related to landform, right, topographic wetness index, and some other things that we can predict spatially, right? When we modeled AGB for most cover types, but then when we're starting to model carbon, we narrow the landscape further down only to what we call forested pixels, and for our purposes, that's tree cover, grass, shrub, and wetlands. Why grass, shrub? Well, disturbance cycles in forests, when you use an annual land use land cover product like LCMAP, which is what we use, right? When a forest is harvested or if there's a blowdown or something, it goes to grass shrub for a while and then kicks back to forest. For a variety of reasons I won't get into, it creates a mess when especially when you're doing the post-processing for greenhouse gas inventory. There's also a lot of areas that are mapped as wetlands that are forested, right? And so this is meant to be more inclusive definition, and certainly is arguable, and this can be filtered down at any particular point in time, any year, any pixel, based on the land use land cover information you have. You can make decisions about what to include or exclude in a map or in any kind of analysis, so there's a lot of flexibility. Just to show you really quickly, and these don't show up super great, here's an AGB map. Notice that you don't see as much variation in this map, and I'm sorry for the quality of the image, didn't come out so great here. From this, we made AGC, BGC, right? We use the AGB prediction in these three models, but there's other variables involved in those models. And just to show you a bit more closely, the reason why these look the way they do is because they're all on the same scale. And notice what map is popping? The soil carbon map is popping because it pushes, right, out to 300. Right? And just to give you a sense, right, these are allometric fits. They're really nice. They make you very happy until you realize that they're just allometric fits. And then you look at the amount of data we have to work with for dead wood, litter, and soil is lonesome, right? For modeling purposes. Again, does this map pass the smell test? I'll show you a bigger version of it. You can decide whether it does or not. So here's AGB to AGC. It's pretty straightforward conversion. It's roughly half, right? A lot of that variation just isn't coming out because of the contrast of the map, but it's there. There's the soil carbon. The patterns here are largely meaningless. This has a lot to do with elevation and slope, right? And some other variables, okay? And so whether the soil carbon map passes the smell test or not matters to me. I don't hate it. I'm not buying it an engagement ring. I'm already married anyways. So, but we did it. And we did it in part because this is one of these things where we need to cover all the bases. More importantly, what this movie is showing is this landscape passing through the last 30 years or so. And it's not super intuitive, but one of the things you'll see is you'll see some changes taking place in some different parts of this landscape. This is all forest preserve up here, and it just reset, right? So what we've been able to do is reconstruct the history of the entire land. I have this for all of New York State, right? Above ground biomass, live carbon in this case, right? Conversions are relatively straightforward and flexible, right? And of course, because we're working with an annual land use land cover product, we can show how that changes too. And we can integrate that into a greenhouse gas inventory to say this forest that was at 120 metric tons per hectare, right, of live carbon, or maybe 400 metric tons per hectare of total carbon, we lost this forest in 1998. It was converted to a Walmart or something else, right? And that's a net emission to the atmosphere in a greenhouse gas inventory framework. So we can track all of this at these 30 meter pixel levels. Again, very practical, right? So this is a stack of maps, right? Just a raster stack, right? Which we can then do all kinds of fun things with, right? We can do simple differencing and look at net biomass changes. We have done some trend analysis where we use a Mann-Kendall and Thiel-Sen analysis, which is a non-parametric trend. Let's just pick out the pixels that consistently have an upward climb in biomass over a 30-year period, and then based on those, we can estimate that rate with a sun slope and get a sense of a growth rate. We can also do temporal segmentation with our outputs, again with Land Trender, and identify the year of greatest loss, percent loss to disturbance, There's lots of things we can do with it, right? And so with these raster stacks, this is fundamentally the guts of this stock change approach. And that gets us to this map of stock changes across New York State and live carbon with some zooming in. And again, I apologize. Sometimes, we produce these really high-res maps, but then when they go through the projectors or PowerPoint, they don't come out as beautiful. But one of the things you notice here a little bit close to home here is this portion of the Catskills Park that was added to the park, I believe, in the 90s, has some of the fastest growth in the state as this forest is regenerated, right? But you can see, and again, I apologize for the color in some cases, right? But where the brown is showing that we've had a net loss of live carbon on the landscape. Now, some of that is managed forest, right? And some of that wood, right, went into things. It didn't just go poof back to the atmosphere, right? There's benefits of harvested wood products, and I know that's a hot topic. I'm not going to wade into that. But this is just showing what happened on the land. It doesn't account for the full life cycle of those harvested wood products. And increasingly, those products can be used to build 12, 20, 30-story buildings, like mass timber construction, right? Like this beautiful structure here, right? Not only does the carbon embodied in that not go to the atmosphere, but the steel and plastic and concrete that we didn't use, don't look at the walls, look up, right? Means emissions that didn't also get released. So there's a substitution benefit of wood products as well, right? And there are implications of harvesting wood from forests for a variety of reasons. All I'm saying is this reflects what happens on the land. It's not a full accounting. Because some of this land was land that was converted from forest to something else. And then that carbon goes poof, right? Unless some of that wood was used for something, but often, sadly, it isn't, as Winslow and I were talking about before, right? So, here we are again. Let's zoom into a place that's actually somewhat intuitive. This is the Upper Hudson Woodlands. It's former Finch Prine land. Finch Prine has a mill in Glens Falls, big paper mill, right? Now we're looking at the scale of something reasonable here. Here's the road passing through. And this is showing this map view. We're stepping through the years. And then this is summarizing the AGB. The land changed hands, was harvested in 2010. You can see the spatial pattern, the timing of harvest, the magnitude of harvest, the recovery from the harvest as the land regenerated, right? You can also, if you're keen to observe, you see this little dip right here? We had an FTC defoliation in 2006 in this area. This has an impact on our statewide assessments. Did forest tent caterpillar kill these trees? No, but it knocked their canopies back. So our models are like, uh-oh, right? And then they bounce back. This is something we have to be able to identify so we can fix it. Because it's not an actual biomass change. It's really a greenness change. The other issue that we've identified from this is that the regeneration rate, again, this is the whole map. So this bounce back includes the pixels that are just still growing that weren't cut, right? But even when we look at the ones that were cut and the bounce back from them, it's a little fast in that first 10 to 15 years. And then when we get to about 15 years, it matches rates from both FIA, which are limited, but the long-term harvesting experiments that Ralph Nyland and other pioneers in the field of northern hardwood forestry have done at our college properties and elsewhere. We have data from cuts put in the 40s and 50s, and well before that, where we can look at those regeneration over long time frames. The idea here is this provides a basis for monitoring. As new Landsat data becomes available, we add another year to the stack, right? We add another map to the stack, and we keep watching what's going on out there. Just to point out, get this for the whole state of New York, including where you live too. The forest industry has vigorously opposed DEC's attempts to have a harvest notification program in New York State. And so when we set out on this project, that was a big subject of conversation. It'll come back up again, I'm sure. So we told the forest industry, who've actually been great partners with us, and I'll share that in a minute, we told them, well, we'll just watch you from space. And they're like, okay, right? So we're capturing the known patterns of disturbance. So we have harvest records and maps, the polygons, the species removal by grade, the timing, the prescription, for almost 400,000 acres of the Adirondacks from working forest, from industrial partners. And when we overlay those with our map series, we see that we're capturing, right, these patterns of harvest, as well as even the differences between heavy cuts and more partial cuts, and their timing and their return. This rate of return is something we have to look at, but the fact that it's regenerating again is critical. That's the difference, right? Forestry is about cutting trees and growing them back again. Deforestation is about just cutting trees and walking away, right? And that is a distinction that I think a lot of people in this state have never had, or it would benefit for some folks to think about more. Very briefly, we can take all of this, and have taken all of this, right? And looked at the last 30 years at a pixel level, and then trained time series forecasting models to then project the next 30 years. So we have, just like we have 30 years of annual maps of the past, we have 30 years of maps, well, starting in 2020, obviously it's 2024, I'm aware of that, but going forward out to 2050, okay? Lots of different scenarios possible, lots of different models possible, can give you lots of different kinds of results. It's kind of like one of these things with time series forecasting. Pick which one you like, right? I don't know, there's no way to really validate it. And really what's nice about this is we can incorporate future land use land cover scenarios, such as those developed by John Thompson and the guys at Harvard Forest and others. Some of you may do this work as well. Simulating future land use land cover change, we can incorporate in that, and that gives us a basis for scenario analysis, just to say business as usual if this forest just keeps doing what it's been doing over the last 30 years. But really, right, forests don't operate, they're not pixels. If there's any unit that makes sense, it's a stand, right? Whatever that is, I used to think I knew, but the further I get into this work, I'm less and less sure what a stand actually is, especially in northern hardwood forests. But what we need is really more simulations, but we have to find a way to impute those simulations to the maps, or have the maps inform the simulations. And maybe there could, I know that Charlie Canham's done some amazing work with sortie and FIA plots, and he and I have talked, and maybe we'll talk again soon about imputing some of those simulations to our maps. I do have a student, I'm not going to talk about it today, but doing a gradient nearest neighbor imputation at FIA plots to pixels across the state for species mapping, so maybe there's some opportunities there. But I'm just briefly touching on that we have this capability, and we provided some business as usual scenarios to the state. When we take all of these maps and we put them in for greenhouse gas inventory, this is this very prescriptive process that the IPCC gives us for doing to produce the kind of numbers that we need. Net emissions or removals of CO2, right? It combines the stock change rasters, our annual LULC products, and stock change reference data. We have done everything we can to replicate this method. I don't have a certificate from IPCC that this is IPCC approved or IPCC certified. I don't know if they do that. But we've done everything we can. And what we find is when we compare, for example, for the last 10 years, total carbon stocks, right? FIA is here and we're here. So we're below them, right? But pretty close, at least in the petagram world, right? And we're pretty consistently different from them, which is helpful. When you actually look at the net fluxes over the last 10 years, FIA has this beautifully smooth line, which I can tell you is controversial in some circles. We're kind of bouncing it around it because we're accounting for annual land use land cover change and other things that are taking place. But we are right where they are. So when we aggregate our data up to the state level, right, this kind of gut check, right, we are right about where they are, which is good. Now, we're not trying to replace their state level stuff, but this is the only scale at which we can make this comparison right now. There's a few counties we could do it for too, but, right? The upshot of this is we can now do this for arbitrary land areas. Does anybody recognize this area? Off the top of your head, this is Fort Drum. This is the last big military base left in New York State. This is home of the 10th Mountain Division, right? There's some pretty badass folks that work up here, and they fly A-10s and they drop all kinds of bombs in here and stuff, right? We can do this for this whole area and have done this where we've reconstructed not only the changes in the forest, right, over time, but the changes in the cantonment area and the airfield over time, which have led to a lot of emissions just from the land. I'm not talking about their jets and their bombs and their tanks and all that stuff. I'm just talking about their land management. So we've been working with the land managers. Upshot of this is we can again convert this for them, and they're getting guidance from the Joint Chiefs and from the White House to minimize their carbon footprint as much as possible. All the bases are. And Fort Drum's trying to be the head of the proverbial spear on this. And you probably didn't hear about this, but Fort Drum is right there near Watertown. They get that lake effect. Back in the 90s, there was a rule that came down from the Army that said we're not going to have snowplows anymore. And the Fort Drum folks didn't get ahead of it, and they really wish they would have. They were literally using APCs and tanks to clear snow for 3 years until they cleared the Pentagon's red tape. So they want to get ahead of this stuff. The upshot of all of this is we can track these carbon stocks over time, and then when you're below, and I apologize, this should say net CO2 flux. We're below this line, it's a net sink, and above this line, it's a net source, and you can see how that's played out over time. So we can provide a greenhouse gas inventory assessment for any given area in New York State. However, there's a lot of uncertainty with all of this, right? It's only a model, right? Or it's a lot of models, right? And what's the first rule of modeling? All models are wrong, right? But some models are useful, right? And so the question is, how wrong are we, right? So the first thing we do is when we're training our models, we need, there's hyperparameters, there's all kinds of different options, there's different observation sets, there's a lot of different things that we can do there, right? We have a 70-30 training holdout, so we take 70% of our data, we use it to train the model, we use the other 30% to test if the model did its thing and how well it did its thing. So there's a lot of testing that goes on here, okay? Once we pick models to make maps, we then check the maps back against the FIA plots, plot to pixel relationships, which is a brutal, brutal test of any type of raster that you produce. We also reference it back against FIA's 60,000 hectare hexagons. These are these Menlove and Healy hexagons, which are very small area estimates that are very controversial, even within the FIA system, because there aren't enough plots to make an estimate here based on FIA's original design. We also do something completely new, which is where we've tried to account for all of the uncertainty we can account for and provide a pixel level uncertainty that's scalable for our maps. And so we bootstrapped a lot of these different sources of error, and ultimately, and I'll talk about this more in a second, this provides an estimate of standard error for any given map unit that you might want to summarize. So, back to the map uncertainty, right? We look at plot to pixel comparisons, and then we aggregate them up at multiple scales by these different aggregation hexagons, right? And we look at our models. This is some of the earlier results from direct training, indirect training, ensemble. You see that wall right there? That's that threshold that model can't predict, right? Above 200, right? Whereas the indirect ones get us up to about 280, right? The ensemble sees a combination of improvements of both. But again, we can look at the relative agreement between our information and FIA information at different scales. We can also, again, look at how our estimates, once adjusted for land cover, align with what FIA would say for these small hexagons. Small hexagons, they're not very small, right? They're 60,000 acres each. This, by the way, this is, we got 92% of them fall within that. But look at how big the confidence intervals are, because there's only a handful of plots in each hexagon that are forested. So that creates some challenges. The more novel work that Lucas Johnson, a PhD student who just defended, Dr. Lucas Johnson, well, I guess he hasn't officially graduated yet, but is this pixel level uncertainty where we compiled all of these different sources, plot location, plot measurement error, allometric models, our own model residuals, and the covariance of those residuals, the spatial autocorrelation of those residuals, to generate like a coincident with each AGB prediction, each pixel, an estimate of different estimates of variability, and then look at how those estimates of variability and the total overall variability compiled into a standard error, which is just a plus or minus. So if I tell you it's 10 plus or minus 2, it could be between 8 and 12, right? But how a standard error comes about and how that varies by parcel size, right? That gives us the ability to now estimate standard error for our maps for every single parcel in the state. In fact, he found that there were a handful of variables around parcel size, shape, perimeter, where we're landing in the AGB or other distribution that allowed him to fit a nice model here. So now we just feed in those parameters for the, right? We don't have to do the full calculation. And this is, the R-square on this is I think 0.96 or 0.98. The idea being is that now we can not only give an estimate, so this is summarized by parcels. You see the little random, right, squares and rectangles and such? This is now an AGB by parcel, right? And this is a standard error for that AGB estimate, which we think the standard errors are much more intuitive than giving someone, a root mean square error or some other metric that we typically would find in the scientific literature. If I tell you you've got 80 metric tons of carbon per acre on your land, plus or minus 10, right, then you know it's between 70 and 90. I think that's good enough. Generally, what we found is that at 50 acres and above, our standard error estimates are they're less than 10% of the statewide mean level of AGB. And so the standard errors are reasonable. However, when you implement them at a larger scale, that's per pixel, right? Here's this site again, here's that path that we followed over time. I'm not running the movie, right? And when you use those standard errors to give us a prediction interval, you now have a wide range of things. And this fundamentally gets to an issue that I don't think is unique to our work, right? Can we reliably estimate stock changes when uncertainty is greater than the rate of change itself, right? And a hat tip to John Battles, who worked with us on this, who was an external advisor. He said our stuff was best in class, and those of you who know him know he doesn't suffer fools and he doesn't offer compliments that he doesn't mean, usually, unless he's getting soft in his old age, which I don't think he is. There's a lot of room for interpretation here, so you could interpret this and say, oh, well, there's this maximum growth, right? Or you could look at it and say there's no growth within that range, right? It's flat, right? Our best guess is something probably like this. We know that our models underestimate the severity of harvest, and we also know that our models overestimate the rate of recovery. We know that from comparing it with data. I haven't shown you all that evidence today. You'll just take my word for it. But this is our best estimate within that prediction space. Obviously, a lot of room for improvement, but maybe let's not let the perfect be the enemy of the good, at least for now. We have some reasonable estimates, and we understand they align numerically as well as everything that we know what's going on here. Yeah, so I'm going to zip through this stuff really quickly just to give you some sense. All of this work that I've shown you is really dependent on our ability to detect and understand landscape change. And we're using Land Trender on Google Earth Engine, which is available for you to use freely. That's LTGEE. We've tuned it against hundreds of thousands of acres of harvest records and other records, forest health flights, for different purposes, because Land Trender was originally developed in the PNW, where they have even age disturbance regimes, very different landscape, right? And so we tuned it and saw some improvements. This map just shows all of the working forest lands we had data for, maps and records for. It's a really, really valuable thing to get and a very hard thing for most academics to get. And this is just showing that the defaults that Land Trender is loaded on the Google Earth Engine, once we tuned it, we were much more effective at detecting harvests in some areas. And so that's really helpful. But then you also, once you detect a disturbance, you need to try to determine what it's caused by. And particularly for the purposes of carbon markets and regulations and so forth, whether a disturbance was a harvest or not is a fundamentally important question. And so we had a patch level classification. We have a model that's at a patch level classifying harvest versus non-harvest. And this is just highlighting the green area as forest preserve. So we'd expect all of those disturbances to be natural, right? And then on the working lands, there can be both natural and harvest disturbances, because on the forest preserve, right, harvest is prohibited and for the most part does not take place. Overall, you'll just have to take my word for this. If you're not used to looking at classification results, you can think of this as a percentile like you would on a paper. So we got like a 93 in accuracy. Overall, the F1 score is an overall, so maybe a 94 in accuracy, right? This is a really nice statistic here. But we are still predicting some portions of disturbance on public land as harvests. And either the park agency really needs to get their ass into gear and catch these people, or our model's wrong, and I think it's probably the latter. But we're making progress on that front, and that's really important, in part because working forest landowners should not be penalized for harvests that they didn't commit, right? Or if you've agreed not to harvest your land, if you've engaged in family forest carbon program or any kind of easement or offset that you say, I promise not to do this for 10 years, and then we're monitoring you, and we see something happen, it'd be helpful for us to be, you still have to go out into the field, obviously, but it would be helpful for us to be able to say, does this look like insect kill or something else? Or does this look like a harvest? Or God forbid, does this look like a land use change? That's the problem with 480A, but don't get me started on that. We can also, right, cross-validate our maps with DEC's aerial forest health maps. And this is an area I'm really excited to get into more so that we can better map and identify these forest health events, because certainly climate matters, but the big threats to our forests right now are bugs and pathogens, and they continue to be. And we need to understand what's going on out there. So there's a lot of potential. To climate solutions, we can summarize all this information by any arbitrary map unit, including, we have a statewide tax parcel database that we get from the government, and we can summarize, this is the change in live carbon over the last 30 years by parcel, right? Hopefully, those of you who are familiar with this kind of space, right, the value for this, for screening and prioritizing parcels for enrollment in programs, right, for easements, land trust acquisitions, offset, it's huge. The response that we've gotten, both from public and private sectors around this, has been huge. TNC, Open Space Institute, DEC, you name it. We are also providing the MMRV, that's the Measurement, Monitoring, Reporting, and Verification, for the forestry side of a USDA Climate Smart Commodities grant that New York State received, where we're, putting, it's a $60 million award. We're putting $13 million into the hands of landowners, forest landowners in New York State over the next 5 or so years through an expanded Regenerate New York program to implement climate smart forest practices, mostly stand improvement and deer exclosures like slash walls and that kind of stuff. And we're going to be able to monitor them as time goes on. One of the reasons why we got this award was Chuck Schumer, of course, right? But another reason why we got this award was because we actually had built what I just showed you and could demonstrate to USDA that we had some idea what the heck we were doing here. Most people have no idea what they're doing for MMRV, right? And there's billions of dollars have been put into these projects across the country. So at least we had something we could like throw at the wall, and it's stuck on the wall long enough for us to get the money. We'll see if it stays there. One of my personal crusades is I hate seeing forests get knocked down for anything, but especially when we're trying to knock them down for good, when we're trying to do good things like solar farms or wind farms or other renewable energy. So this year, the governor fast-tracked NYSERDA's solar scorecard process. This is NYSERDA subsidizing solar facilities in New York State. This precluded them from doing any field work, and we were able to jump in and evaluate solar facilities for their solar scorecard to try to disincentivize or at least not subsidize forest clearing for solar, right? And several of our map layers were used to score these proposals. These are not the ones we use. These were built a long time ago, and I can show them to you. They're not confidential. But what's cool about this is Long Island Solar Farm was built in 2011. So we went back to 2010 and said, what was the live carbon there then? What was the carbon debt that was incurred from clearing that land, right? The Shoreham, which is also, I believe, on Long Island, was not forested at all before it was built, which is why that map looks blank, right? So if you're going to subsidize one of these two projects, which one are you going to pick, right? Well, probably not based on data, but at least we're trying to provide them that kind of information. We evaluated 55 proposals in 48 hours over a weekend just by taking the polygons they gave us and firing them into our database. We're up for 2024, and we're going to probably stay in this process going forward. We also did it for free, which some of my colleagues tell me is insane, right? All right, last part. And I apologize, I'm running a couple of minutes long, but I hope I still have you. Here's a few questions. I do still care about questions. Like, I am still very interested in questions, right? So all of this work, it's been objective driven. Like, how do we get here? How do we get here? How do we produce this? Oh, this is good enough. This looks okay. I'm not crazy about this, right? I do still care about questions, and I know all of you care about questions. You're driven by questions. You do some of the best work in the world around ecological questions, right? And these may not necessarily be fundamental ecological questions that are going to get me a paper in, ecology letters or PNAS, but there's some things that we've looked at from this work. So by reconstructing the disturbance history of the whole landscape, one of the questions we can ask is, are forest disturbance regimes changing? So we looked at the forest preserve of the Adirondacks. This is about 2.7 million acres of land that is free from direct forms of human disturbance. I say direct. I mean chainsaws, skidders, right, that kind of thing. Acid rain, climate change, mercury pollution, I mean, the list goes on, right? It still affects this land. We looked at, right, trends in patch and landscape metrics going back to 1990. That is a very short period of time in terms of the return interval of stand replacing disturbances, right? I believe Charlie Canham has, based on FIA, has estimated the stand replacing disturbance interval in northern hardwood forest to be on the order of millennia, not decades or centuries, right? But we're not talking about stand replacement, we're talking about even gaps, right? We're talking about the normal kinds of processes that these forests go through. We found since 1990 is over 90% of patches were less than a hectare in size, which is consistent with what we'd expect in this landscape, right? These forests are not that old. Most of them, at most, are about 150 years old, right? And a lot of them are younger than that and have some, they're uneven aged. We were expecting to find evidence of an intensifying disturbance regime. How many of you would expect that, right? That's what you've heard about, right? That's what we've been told about for decades. You know, that things are just going to get crazier and we're going to see increased rates of tree mortality, right? There's a lot of science and a lot of policy interpretation of science that says that. We found that there's a decreasing percent area disturbed each year in the Adirondack Forest Preserve since 1990, and that there's no difference in patch sizes. There's more distance between the patches, which just means there's fewer patches every year. Disturbance. And what's going on here? Is it a foreboding of the future? I don't know. But especially since 2008, look at that. There's like there might be a regime shift there, just qualitatively. Is that likely to last? Probably not. Hemlock woolly adelgid is on the way, right? And that's going to make a big difference. But it is interesting to look at that. Another question is, does harvesting emulate natural disturbance? And we're just really talking from the landscape perspective. Really not ecologically, right? There's a lot of things that harvesting can't because you remove the material from the site, right? The natural disturbance, especially things like the typical ice and wind throw that happens in these forests, right? But as part of the modeling process to do an attribution model where we could classify disturbances as harvest or non-harvest, right? We looked at all these parameters. This is what we fed the model. We found the spatial property of harvest patches are pretty similar to natural disturbances. Right, so these natural disturbances were ones that we mapped in the forest preserve, so we know they're not harvest. We know these are harvest because we have all the harvest records and maps from the landowners they gave us. These, for the most part, with the exception, you can't see the yellow because it matches up with the blue. The distributions of these things are very similar. So spatially, harvests look a lot like natural disturbances, which isn't surprising if you know anything about northern hardwood forestry. Like in the Adirondacks. Again, this is based on the Adirondacks. Spectrally, they're very different though. And this is actually what our models grab hold of, are these differences in spectral properties. And these are different indices. This is normalized burn ratio, NDVI, normalized difference of vegetation index, tassel cap brightness, tassel cap wetness, some of these different Landsat-derived spectral indices. And what we see is that natural disturbances tend to occupy a range of spectral characteristics, whereas harvests are very narrowly in a particular space. And we're thinking more about what this means, and anybody who's interested, I would love to talk about this more. Lastly, the big question, and I was hoping Charlie would be here for this, but he's in a parking lot listening somewhere. I've been asked by a lot of people to do this, and this is one of the first times I've ever presented it. And I'm far enough away from the Adirondacks not to get hit by anybody, hopefully. This question, are working forests better carbon sinks, or are reserves better carbon sinks? That old trees versus young trees, right? That debate. Charlie and colleagues Bob Momsheimer at ESF, everybody's tried to bring me into this debate. And my answer has always been, let's just have more forest. Right? That's a cop-out, but it's also my way of saying this is too complicated, it's too contextual. But we can start to think about this, right? And to the extent that this work is useful in answering questions about this, we can compare for the last 30 years the forest preserve in green working forests, right, which are shown in the resource management lands, right, in blue, and other private lands in red. This is one way to split the landscape up 3 ways, right? Reserves have higher carbon density than working lands. That makes sense, right? They're not being harvested, right? This dip, the Adirondacks got hit multiple years, like I said, by an FTC defoliation. This is a problem with our models because our models see this as a loss of biomass, but it's not really a loss of biomass, right? But that's something why we need to be able to identify these things so we can fix this. The important take-home message here, it doesn't matter how much carbon you have when you're talking about being a carbon sink, it matters how much you're taking in each year. And especially when you look at since 2008, right, the last 10, 12 years of this time series, that rate of change is almost identical. The working lands and the reserves are both killing it out there. They're both sequestering carbon at similar rates. The old expression, you can't have your cake and eat it too, does not apply to landscapes. You can have both, right? And we do have both. The question of whether one of these is a better strategy or not is a great question, and this can't answer it entirely. But it does suggest that maybe we shouldn't be answering this question based solely on carbon information. There's many, 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 many other arguably more important and certainly more interesting values of forests than just their carbon sequestration, right? But when it comes to this, the answer is still like, they're about the same. And maybe we're wrong, but I think that's really compelling. We have a lot of data products that we produce, happy to share them. Especially for partners in the scientific world. For private sector partners, they have to sign data use agreements, trying to minimize the misuse of this data, both for illegal harvesting of timber, because you can see where the volume is, or kind of the poaching where people, you've got these bands of unscrupulous loggers out there, I guess. They'll knock on doors and say, give somebody, I'll give you $25,000 for the wood on your lot when it's actually worth $100,000. Worse than that, they beat it up and they don't manage it sustainably, and it leads to a much worse outcome. I also don't want the data weaponized by advocacy groups or by individual citizens against each other. You can reconstruct the history of the landscape, you can see what people did. But we're happy to share it for academic and scientific purposes. And again, this whole thing is built to go forward in time. Oh, I did the thing that I wasn't going to do. And it's built on open source. And so it's meant to run forward and be upgradable, but it is, and I apologize, I've gone way over time. Sorry, Shannon. But that's the end of my talk. Thank you so much.
Thank you for the talk. Now, I recognize that people will need to go. It's noon, but we have time. We'll take time for one question now, and then Dr. Beier will join us in the lunchroom for the next hour.
Yes.
When thinking about the carbon offsets for New York State, how do you separate out what would have naturally been sequestered versus what's additional?
That's a great question, and I don't have a great answer for that. I think the additionality question is really tricky. So is the leakage stuff. And I think that some of this information can help us get to some of those answers, I think. But as I understand it now, right, you don't get credit, right, for anything that you've done. It's about what you do next, right? And I think it's really interesting. It's one of the only markets that has so many strictures on it. You got between leakage and additionality, the carbon benefits, the carbon offsets are basically untenable. And then in a state like New York, landowners don't want to be locked into something for a long period of time, right? They want to have options. And so offsets are very unpopular in New York State, and I think likely will continue to be. That doesn't get to your question. I think, how do we determine that? Well, I think you'd need to know what each individual landowner's rationale for their decision would be. Does that make sense? And I certainly can't map that, right? So, but I think it's a great question. I think that one of the things, this is most likely going to be a losing battle, but I think that to the extent that this work has any value, it represents a biophysical reality, right? For example, ESF has 25,000 acres of forest land. The sequestration on that land more than offsets our emissions from what is largely a wood-burning facility on campus that powers our campus, right? We still get some steam from Syracuse University, right? But the sequestration on our lands more than offsets. But according to the kind of carbon offset in the higher ed world, unless we deliberately did things differently, we don't get credit for any of that. And that's fine, but there is still a biophysical reality of like, we're emitting this much and we're taking in this much, and if we wanted to, we could sell that land. We're not going to, but the average landowner will. They will succumb to that development pressure. And that's especially true here in the lower Hudson Valley. Based on FIA, your growth to removal ratios in the lower Hudson Valley are pushing 6 to 1. There is literally nowhere for landowners to remove low-grade wood from their land to improve their stand. There's no markets for it. So there's no way to sustainably manage the land unless you're wealthy, right, and generate any revenue from it. So what are those landowners going to do? They're going to sell. Are they going to sell for the forest rights and the forest value? No, they're going to sell for the development rights. They're going to subdivide and sell. And it's going to go to residential or sprawl or solar or wind or whatever it might be. And the first rule here is you got to play defense. You can't lose forest land. There's no hope of us getting where we need to go if the state continues to lose forest land. One thing I didn't mention, and I'll stop there because I could obviously talk about this forever. The reason why our carbon sink, it was in 1990, they estimated it was 30 million metric tons. We need to get to 60, right? We were at 30. It's gotten smaller because of deforestation. A little bit every year. It's like death by 1,000 cuts. We're losing anywhere from 1,000 to 5,000 acres of forest roughly a year in New York State. It's just a little bit here and there, right? And most of it's going to development. It's not going to ag, right? What's starting to show up on there is solar starting to show up. And I'm hearing from soil and water conservation districts, I'm hearing from private citizens, I'm hearing from a lot of other folks that there's a lot of solar plan that's going to clear a lot of forest land. And so that's an area that we're trying to lean in a constructive way and try to minimize that kind of outcome. Anyways, I got way off your question, sorry. Thank you all for bearing with me. I apologize for going long.